So let me start today's lecture by just quickly mentioning an issue related to what we have been doing, and that is the sample size, population size correction. So in all the formulas which we have used so far in estimating the confidence interval, we have been assuming a very large population. So we have been assuming that the sample is much smaller than the population. Uh, and as you know, as we have discussed previously, that when the population is finite, then there is a small correction there is a correction to various formulas. And when in those formulas, when you take n to be very large, they reduce to much simpler formulas, which we usually use when we have a large population. So if you recall, like mainly we have been using this formula. Like if you are estimating confidence interval for a mean, for the mean of population, then we have this thing, that the interval is that whatever mean you compute using your sample plus a margin of error, which is equal to, you have this normal variable, standard normal variable, with a given uh, acceptance, given probability, and this is multiplied by the uh, the standard deviation of the sample, which is equal to, if you know the standard deviation of population, then the correct formula to put in over here is just, you take this standard deviation of the population and make it corrected by square root of n, because this is then equal to, we know that we are assuming that our sample mean, it is a normal, it acts like a normal variable. We are not assuming it is always true. It's a normal variable whose standard deviation is just, you take the population standard deviation and divide it by square root of n. So this is the formula if you know the standard deviation of the population. If you don't know the standard deviation of the population, then we know that this, then we can estimate. This is then gives you the confidence interval around your uh, mean calculated from a single sample. And instead of this thing, you estimate this using your sample. And we know that the sample standard deviation, it has the average equal to this population standard deviation. So you just estimate by that. So in this formula, instead of having population standard deviation, you put in the sample standard deviation. But because this guy is a random variable itself, that changes the distribution slightly. And instead of having the standard normal here, you have this t distribution, which is very close to the standard normal, but not exactly that. When n becomes large, it looks more and more like the standard normal. So that's the main formula which we have been using. Now
सर
the
ये
yeah
ये फॉर्मूला कब यूज होता है जब एज वो पॉपुलेशन स्टैंडर्ड डेविएशन पता नहीं हो तब
हाँ
यूज होता
पता नहीं होती, and practically speaking this would be most likely situation. This will be very rare in practice, that you do not know the mean of the population, but somehow you know the standard deviation of the population. So this is the most used and most practical formula. But this is handy to know because it gives you the idea that how we are building up our logic. So now the idea is that if you have a finite population, then we know that this guy, its average is not equal to sigma over under root n, rather it's corrected with this term. So you just take this correction, and this confidence interval then becomes alpha, and instead of having only under root n here, you have this correction. So that's the only thing. If and how do you know when you're going to use it? If you know that this number for the number in the population, total elements in the population, and this is your sample size. This is the population size. If you compute this number and this is significant, so that it's changing your result to your desired accuracy, within your desired accuracy level, then you would like to put in this. But if the population is very large, or you are just drawing from a supposed probability distribution, then you don't have to include this factor. So similarly, you can correct for other confidence interval estimates as well. For example, if you are estimating the population, similarly for, let's say, population proportion. Now over there, again, we have the confidence of interval is given by, you just estimate it by the sample proportion, but you build around it an interval, because again the sample proportion behaves like a normal variable. That's why this standard normal comes in here, and here you just include the standard deviation of the uh, sample proportion. Exactly this logic, exactly same logic. Deviation of sample proportion. Now, previously we took this because we have seen these formulas in previous chapter as well. It is just this thing. But that formula is true because there's no mention of population size in this formula. When you have a finite population, this is corrected by this, just like over here. Yeah, this was right now we are on chapter 7, and original formulas we derived in, or at least discussed in chapter 6, these correction formulas. So you do exactly the same thing, but
Sir,
wait a minute. But you do exactly the same thing which we did last time for the confidence interval for population proportion. Just that instead of using this formula, which goes in here, so the margin of error is Z alpha by 2. This, now it all depends. If you are taking it to be a large population, then you only include this. But if it's a finite population or a small population, then you have to include this finite population correction. Yeah, what's the question?
Sir, I think last time we just used to do like standard deviation divided by root n. The last time we did, and now there's something different.
No, that's what I'm doing. But that we didn't do it for the population proportion. I think you missed the last lecture. When you're doing the population proportion is uh, is a normal variable. But the population proportion is standard deviation is not this, because that's a completely different thing. This thing, if you have a population whose standard deviation is sigma, then the sample mean is a normal variable whose standard deviation is sigma over under root n. This is true for the sample mean, but not for the sample proportion. Sample proportion is also a normal variable. However, its standard deviation is this. Where P in principle is the population proportion, but you can estimate it by the sample proportion itself. That's
Yes,
the
sir. I know this. I wanted to
yeah.
know what's capital N minus n divided by capital N minus 1 into half. Why are we doing that?
I'm just that's what I have been explaining. It's the finite population correction. If you have a finite population,
Oh,
then
okay, sir. Thank you.
this is changed. So you can go through the list of various formulas, and all you are doing is that when you include, because in all of them, the main idea is that your random variable which you are constructing, sampling, is a normal variable. So you're using some kind of this kind of formula, some form of this kind of formula. So there is a standard deviation associated with it, and it's all about what is the formula for standard deviation. And this formula for standard deviation for finite populations may be changed, and then you just use that formula. So similarly for sample size, well, yeah, so let me now just go into that. So if you're estimating, for example, sample size, where we said that we know the standard deviation of the population, then we said that you have a sample mean whose uh, variance is given by this. And we said that we will compute that what n we need to get a certain margin of error using this formula. And from here, we said we will compute beforehand what we need for a given margin of error, how big of a sample size of sample we will need. So you can use the same formula. Just remember that this sigma. So right now we started from this. So when we are using a finite sample, then this thing changes. This thing changes how? By this finite size correction. So this changes to, let me use another color. this one. And from here, you will have this. So from here, you can solve for this small n, and you can use that formula. Now, with this mention, is there any question about any of this? Let me come to today's main topic, and that is confidence interval. This is basically chapter 8 in the book. So now you want to put confidence interval. You want to estimate a confidence interval of the difference between two normal populations. Difference of, let's say, mean or proportion, any of those things. Why would you need this? Well, this is a very commonly occurring problem because many a times you are comparing two things. You're trying to decide which one is better. So for example, you can have two drugs for same condition. Let's say you want to see which one of them controls the sugar levels better in some diabetic patients. So you test one and you compute what is the effect of this, and you want to compare it with the effect of the other drug. Or for example, you can say if people work in the night shifts or day shifts, which of the population is more efficient, which has more productivity. So you want to compute the productivity of night shift and the day shift and compare those two. Comparing means taking a difference. Which one is better? So how would you do it? Well, so one simple idea is that you have one population, let's say population A, and you have population B. Again, the whole idea is that we are doing some statistical analysis. We do not have access to the whole population. You pick a sample here and you compute the mean. You get some mean. Similarly, you pick a sample here, you compute the mean, and you just take the difference. If, let's say, if this is positive, then you know that this effect, from this difference, you can see which one is better for any particular, whatever characteristic you are looking at, which is higher than the other. But we know that we cannot really do that, because once we compute, we pick a sample and we compute a mean. This mean is not the population mean. This is not the mean of the whole population. Similarly, this is not the mean of the whole population B. So we can get, it may be true that mu A is bigger than, for example, mu B, but just by chance, we get this to be less than B. And we know that the best we can do, we have to give some kind of a confidence level. Let's say beta times 100% confidence interval. We always estimate some confidence interval around the mean we calculate using a sample. Similarly, there would be a confidence interval around this. So the question is that how do we subtract these two confidence intervals? Because in the end, based on what we compute here, this difference, we have to give a confidence interval of the population means, because we want to make a statement about the whole population. This difference, we want to give a confidence interval around this using whatever data we have. So the idea is, given this and given this, how to put this confidence interval, how to guess that. Now, in this question, answering this question, again, there will be many possibilities. First of all, it depends that what kind of sample you have. So they could be, for the two populations, they could be dependent samples or independent samples. So what's a dependent sample? So dependent sample would be something like, so you have population A, you pick a sample here, let's say X1, and depending on which one you got here, you have a matched pair in population B, let's say Y1. So this is picked randomly, but this is not completely random. This guy depends on which one you picked here. And so on. So in this case, you call it a dependent sample. So what would be the example? Well, it could be, for example, these population A and B could be same, could be the same population, could consist of same elements under different conditions. So for example, you could say, do students get better grades in spring semester or in fall semester? So what would you do? You would pick a sample of students. So let's say you picked n students. And then population A, the sample A would consist of taking their grades in spring semester, while the sample B would be taking their grades for fall semester, but of the same student. So it's not independent sample. The sampling was not independent. You picked one student and you computed and you looked at their grades in spring and their grades in fall. So similarly, the next student, their grade in spring and their grade in fall. So that would be an example of dependent populations. So in the end, what is the population? Population is grades in spring and grades in fall. But they're not sampled independently. They are sampled in a matched fashion, so that the once you pick an element in the sample from the first population, you know that which one you're going to pick from the second population. I'll come to your question. Let me just say a few things. Maybe it will become clear. There could be let me give you another example. So in this case, it was like same elements working in different conditions, like same student. What happens when they are when we look at their grades in spring or in fall? Or it could be some workers working in night shifts. How is their productivity working in night shift or day shift? So you can pick a sample of workers and look at their productivity when they were assigned a day shift or when they were assigned a night shift. Or another example would be you take two drugs, let's say drug A and drug B. You want to know which one is more effective. You pick patients. So you have picked a sample and you, whatever your value is, however way you are describing the effectiveness, you give them drug A, you get a number X1. So to the same guy, you give the drug B, you get another number. So again, this is not independent sampling, this is dependent sampling. And sometimes this dependent sampling can happen when you're not considering the same subjects or same elements from the population. There may be two different populations, let's say population A, population B, but still somehow they are matched. For example, you can ask that, excuse me, can you wait a minute? Yeah. So for example, you could ask the question that who works more at home, men or women? So you ask a question that for those couples where both husband and wife are working outside the home, who spends more time doing the household chores? So this could be husband. This is wives. Now, what you can do, you can pick a sample of couples. So if you're picking a sample of couples, you get certain number of minutes, let's say, for the husband, and the wife of this very husband, maybe there's a certain number here. So again, this sampling is dependent, the sample in the population B is dependent on which one you picked in the population A. So that would be dependent sampling. In this case, how you do it is fairly easy. So what you do is, let's say, let me write it again. When you have matched pair, so sample 1, sample 2, and they are matched for some reason. Then you can compute, since this is dependent on this, you can just compute a new column of differences. X1 minus Y1 so that your DI is XI minus YI. And then this difference, this becomes because since this is a normal variable and this is a normal variable, this difference column which you have created, this is also a normal variable. So you can just compute the average distance, average difference, which is just the average computed on the differences you computed using your two columns. And since I don't know what is the variance of the population, so I can use this formula. I know that this will be, since it's a normal variable, I can put the confidence interval this way. Where, again, I had to put a standard deviation over here, since I don't know the standard deviation of the population, so I get it from my sample. So it's just the standard deviation of the differences. Within n minus 1. And this is giving you the margin of error. Where again, this n minus 1 is coming from how many data points you had in the sample. And this alpha is related to if you want to put a beta times 100% confidence interval, then 1 minus beta is alpha. And this t, you know it, that it is that critical value for this is greater than, this probability is greater than alpha by 2. And if you are computing the cumulative probabilities, so it's that one for which all tn minus 1 less than these are 1 minus alpha by 2. And this t is as usual. This is the t students t distribution. So any question so far? Now let me do an example, and that will make things clear. So suppose you have two drugs. Let me go to so I lost the data. Let me do this. Okay, let's do this one. So suppose you have some students and they are given, you want to test their, you are giving them a course, a special course, a remedial course on, let's say, their mathematics skills. And you want to test that if there's any effect of this remedial course on their performance or not. So you first give them a test, a standard kind of test, which is written over here, pre-test. And you give them a course and then you give them another test to see if there's a difference or not. So you want to know that what is the difference of this test on a whole population of students, but you have done this experiment only on a finite sample. So here are given the test numbers out of 50 in the p-test. So student 1 had 40, 2 had 36, 32, 38, and so on. And after given the course, these were the numbers on the standardized test again. Now, this is clearly a dependent sampling because it's the same student who is given the test before and after. Same students given the test before and after. So to do this analysis, to find out, put a confidence interval, we want to get a confidence interval, let's say of 95%, that is there an effect of taking this course? So example. Pre-test scores and post-test scores for same students. And find a confidence interval of 95% confidence level. Let's say this way, find a 95% confidence interval for the effect of remedial course on the performance of students. So if you look at this data, like some students improved, but the improvement is obviously different. And there's this student who actually performed worse because it's all statistical. And this is a small sample. You want to make a statement about you are assuming that in the whole class or in the whole university, there is a certain average of the skill level of the students, which if you had given them p-tests, you could have found out, but you're not doing it. You're just picking a small sample. Similarly, if you give this course to all the students, they will probably improve and their test scores will improve, but you are not finding that out. You have just picked a small sample. And based on this small sample, you want to say some statement about the whole population of students. So behind this, there's a belief that the whole population of the students behave in a certain normal way. So how would you then find this interval? Well, these are the formulas we have to use. We have to put a margin of error that will compute for us this interval. But we will need the difference and the average of the difference. Sample mean of the difference. This is a standard critical value, which you will look up from the table. And this you have to again compute from your sample. How would you compute these two numbers? These are the two numbers which we need. You just look at this table, construct this table, and compute these from this table using this formula and this formula. Yeah, there's a question.
Sir, is this T distribution or Z distribution?
It's T distribution because I don't know what is the variance of any of these population. So you can do it using calculator. I'm just gonna do it quickly. I obviously I can't waste class time using calculator, so I'm just doing it on SPSS. So one thing you note in this, I constructed this example deliberately, that there is a possibility, like over here, there was a student who took the pre-test but didn't show up for post-test. Similarly, there was a student who was missing that day and you don't have the data about the pre-test. So you won't be constructing any differences over here. So you cannot use these values in your analysis. They will not show up. So first of all I need to do is I have to compute the difference. So I construct a new variable, difference, and that should be equal to the, I just have to subtract the post-test from the pre-test. And these are the values I get. Now that means effectively I have how many? Four. The sample size is only 5. So the t variable I will be using would be t4. So now what I need to do? I need to compute the mean. So I have to analyze. I go to descriptives. I have to compute the mean of the difference and its sample standard deviation. So mean and standard deviation. Yeah, Shahrukh, you have a question?
सर हम -2 को +2 नहीं कर देंगे since
No,
हम
we won't do it. We won't do it because we want to exactly know if the difference is positive or not. So like, it could be that this course is just confusing them and they're doing even worse. So you want to say if there's a positive effect of this course or not. So when you're computing the difference of the means, that's the main goal today, computing the difference of the means of two populations. You want it with a sign. It's not just, it's a sign difference. So I just take this data, which is written over here, and compute its mean and its standard deviation. So it gives me 5.4 and 4.6. Let me write it over here. So the difference mean is 5.4. So it's telling us the, just looking at this difference, we are getting some kind of an idea, at least this sample, in this sample is showing that at least in this sample, there's a positive effect of this test. However, there's a standard deviation. So this number couldn't be just the overall effect of this test, that this course improves their test scores by 5.4. You can't say it because there's a standard deviation. And how much is that? Is 4.56. Sorry, I just want to write it. Now you have to put it in this formula. So for that, you need this critical value. Let me just create a new data file to store these numbers, 5.4 and 4.56. Let's give them names, mean and standard deviation. And let me compute the critical value. You can look it up in the table. Let me just do it over here. Critical value, go to inverse distribution, the t variable. And as you know that this formula is computing the cumulative distribution. So I have to do 1 minus alpha by 2. Alpha is 0.05. So 1 minus alpha by 2 is 0.975. And since I have only 5 data points, so the number of variables over here is n minus 1. So 5 minus 1 is 4. And you get 2.78 is the critical value. And now all I have to do is put them in this formula to compute the margin of error. So let me do it in this file.
Sir, can you repeat? T-test क्यों use कर रहे हैं?
T-test नहीं use कर रहे. We haven't gone to any T-test. You are getting confused just by the symbols. It's the T variable. We are using T variable because we don't know this the standard deviation of the population. And in whatever I'm doing today, I'm not assuming anything about the standard deviation of the population so far. So this critical value I found. So margin of error I can compute. Let's call it margin of error. And the way you compute is take the critical value of the t variable, multiply it with the standard deviation, and divide by square root of the sample size. And square root I can pick up from here. Sample size is 5. So the margin of error is 5.66. And my mean was 5.4. Excuse me. So my confidence interval what was it? 5.66. So although my sample tells me, my sample gives me an impression that there's an improvement, but at 95%, you cannot say it at 95% level, because at 95% level, the interval turns out to be 5.4 minus 5.66 to 5.4 plus 5.66. So this number becomes minus 0.26 to 5.4 plus 5.66. I'm very bad with numbers. I have to rely on the calculator. So that means the improvement which you see, which you can say reliably at 95% confidence level, for the whole students, if you really want to offer this course, the improvement could be anywhere between 11 and minus 0.26. So it could even be 0, because you don't know what that actual number for population is. What is the average improvement in the students? So the average improvement in the students lies anywhere over here at 95% confidence level, confidence interval. So it could have a positive effect, or it could have no effect, or it could be slightly worse. But so that's all you can conclude based on this. However, if you said that, well, let me go to another example, then I can discuss those things. Let's consider this example. Okay, you want to subscribe to an internet provider and you want to check the speed, that which one is better. They're both saying that our speed is a certain number of MBs per second, and but you know that in practice things don't work that way. So you want to test that which one is better. So you take some standard files you have and you try to download using internet A and internet B. And this is the number of seconds it takes to download that file. Now, this is clearly those two samples are dependent because it's the same file which you are downloading using internet A, internet providers A, and using providers B. So it's again the same problem. And how would you solve it? You are given this data. So again, you have to, all you can do, you can simply do compute the difference of A and B. So this is the difference you get. And then you can analyze it. You're analyzing the difference. You want the mean difference of your sample and the standard deviation of your sample of the difference, standard deviation of the differences of your sample. So you get a mean value of minus 4.2. That means the internet A is taking less time in your sample. But there's a standard deviation. Sometimes it's not really true. So based on this, you want to say, what is the confidence interval? Let's say you want to put it at 95% level. So how would you do it? I don't need to compute that variable because I will be again using this formula. And since I said 95% confidence interval, so I have already computed these values. Well, no, not really, because I have to compute this t variable changes depending on what is the sample size. So this n goes in here. So you have to compute a new critical value. And let's store this data, minus 4.2 and 3.852. Minus 4.2 and 3.852. And I want to compute this critical value. This critical value. And what is this? This is the inverse distribution, 0.975. And the number of variables are, how many there were? Let's wait. Number of variables are 9. because the total data size is 10, so it's one less than that, 9. So compute critical value. .975, and over here you have to put in 9. So it comes out to be 2.26. And now I can compute the margin of error. Which is this critical value times the standard deviation divided by square root of 10. So it's 2.76. That means in this case, my confidence interval of difference is minus 4.2 and around it 2.76. At 95% confidence level. So you can see that even if so what would be the numbers? 4.2 plus 2.76. So minus 6.96. This is the average download difference of the download times, and minus this would be minus 1.4. So both number in this case are negative. So at 95% confidence interval, you can say that the internet provider A is better than internet provider B because it's faster at 95% confidence interval. You don't know how fast exactly, but at 95% confidence interval, it's always taking less time on average. Now let's take another example. So suppose you have drug A. I'm not going to do this example. You can do it. I'm just going to talk about it. So suppose you have drug A and drug B, and they both are for reducing cholesterol levels. And this is the amount by which this is the level of cholesterol in certain units in the person. So you take some patients and for a week give them drug A, and then you stop. And during that week, this is their cholesterol levels. Then you take the same person and in a different week, you give them drug B. And during that week, these are their cholesterol levels. So you want to say that which drug is better in managing their cholesterol level. So now again, this is a dependent data because it's the same same patients you are using. So again, you can compute the difference and you can just compute the average of the difference. And around that average, this average obviously going to come out to be a negative, which is showing that drug A has a better effect. It's reducing the cholesterol level better than B in this sample. But you want to say, make a statement about the population. So you take that average and construct an interval around it, depending on what standard deviation you get for these differences. Now let's take another example, and that will bring us to a different concept. So suppose you want to find out that in a certain city, or in a certain, in general, let's say, who spends more time in doing housework, for those couples where both husbands and wives are working outside the home. So here is some data, and this is the data which is collected for some couples. So you selected 10 couples randomly from the population, and then found out through a survey or whatever method you had available that on average how many minutes per day the husbands spend doing housework and how many minutes the wives spend doing housework. So from this data, like in this sample, it looks like that because the average, this difference is between wife minus husband. So the wives in this sample are doing more housework. But you want to again say something about the whole population. So you have to put a confidence interval. Now, this sample is dependent. These two samples are dependent because you took the same couple and asked them. So the wife appearing here is the wife of this husband. It's not some random woman. And for example, if you look at this data point, this woman is not putting a lot of time at home, at the house, but so is his husband, her husband. And why could it be so? It could be like because they have house help available, they have hired someone, so they don't spend too much time doing homework by themselves. While these guys, they both, husband and wife, are spending a lot of time, maybe they don't have any house help available. So obviously, if you have this matched data, then you have more information about these two populations you are sampling. So here's the population of men, here's the population of women, but they are matched. And because of this matching, you have some extra information, and that reflects in your statistical analysis. But on the other hand, if I hadn't sampled this way, if instead these were just men and these were just women, and the way I had sampled was I was still looking for those men who are married and working outside, and those women who are married and working outside. But I didn't select the couples. I just went out to some workplaces and selected some men on random, and I got these numbers. And I selected women at random, married, still married, working outside with their husbands working outside, but at random. They have no relation to these men. Then this data is not connected. Then if this woman is working less, it's not, I can't say that her husband is also working less, so that the difference is difference of the wife minus husband is still giving me a positive contribution to my statistical analysis. It may be that her husband is working a lot at home and she's working less. That's why I got a smaller number. So in that case, the statistical analysis obviously would be different. I can't be making these differences and make inferences based on that. These then data points are completely random, completely different from these data points. They only reveal information about how much working married women work at home. And this only reveals some information about how much married men working outside they work at home. I cannot correlate them. So I cannot make a difference and then do statistical analysis on the differences. The statistical analysis should be such that they are treated independently. So what to do in that case? So that's our next topic. So I can say that what to do if you want to put a confidence interval of difference of two mean, still we are interested in the same question. Difference of the means of the two populations. Confidence interval of difference of two means, but with independent samples from the two populations. So if I go to previous examples, what could be an independent sampling? So like in this drug example, if I had just taken some patients and given them drug X in the same week, and in the same week I was doing this experiment, I had taken some other patients and given them drug Y, then this would be independent sampling. Similarly, over here, if I had just taken some random files and downloaded them, or maybe this is not very clear. If I go over here, if I had given this course to some students and taken the test afterwards, and had taken a test, given a test to some students who had not taken this course, completely different students, then this would be independent sampling. Then I'm just comparing two populations. One of them have taken a test, and one of them have taken a remedial course, and one of them haven't. And obviously they are different people, they have no relation to each other. So then it would be independent sampling of the two populations. How do you define one who have taken a course and the others who haven't? So what you can do, how should you deal with these cases? Well, you are assuming that you pick samples. So this is sample X, this is sample Y, this is from population X, population Y. Let's make it small. You have some numbers. They're not matched. They don't even have to be equal in number because they have no relation to each other. You may have n from here, n elements in this sample, and m elements in the other sample. But you know that I can compute a mean here. I can compute a mean here. I know that the expectation value of this mean is equal to the two mean of this population, population X. Similarly, expectation value of the mean of the second is equal to the true mean of the second population. So by the properties of the expectation value, if I compute this of the difference, this is just equal to mu x minus mu y. So that means the difference of the two means obviously is a random variable, but it would be because each independently is a normal variable with mean mu x minus mu y and what would be the standard deviation? I know that variance works this way. You whatever is multiplied with the variable comes out squared. So the variance of a difference is actually equal to sum of the individual variances. So this would be the first number, where nx is the size of the first sample, where this is the standard deviation of population x, and this is the standard deviation of population y. So that means the difference would be this normal variable, standard normal. This you get from your samples, x bar minus y bar, and it would be a normal around the true mean, where the standard deviation of this would be this. So I can put confidence interval in this way using the logics which I'm not going to repeat, which we have all derived, that we always do this. We take the mean of our sample. In our sample, the mean, we are taking the difference. Is the sample mean of, is the difference of the two sample means. So that's your estimate, but you correct it with a margin of error. And this margin of error is just going to be, if you know the standard deviation of the populations, it's going to be the standard normal critical value coming in here multiplied by the standard deviation, as I discussed in the beginning of the lecture, which in this case is just this. If you know the standard deviation of the populations of the two populations, which are these, sigma x and sigma y. But obviously in practice, usually it's not gonna be true. You wouldn't be knowing what is the standard deviation of the population. So more often you would be putting it this way. When you don't know, you put a student's t variable. There's some n comes in here, and you pick these guys from your samples, the two samples. And there's an n which comes in here. What n goes in here is because these two samples may have different sizes. So the n which comes in here takes a very specific form. You have to compute it, and that I'll discuss next time. So like if I come back to this example, If they were independent, then I'll have to compute their individual sample standard deviation. That's the main difference. When you will make the differences, the sample mean of the differences would be same as the difference of taking the two sample means. If I take the mean over here of men, take the mean of women, and take the difference, that would be same as taking the mean of these differences. However, taking the standard deviation of the differences is not same as taking the standard deviation of men and taking the standard deviation of women and subtracting them. If they are independent, then I have to compute the standard deviations separately and use this formula. So we will do it next time. So any question?
Sir, can I request if you could shift to physical classes?
But the question is, how many people are going to show up? Because the my only issue is that in the physical classes, I still have to do it just like I'm doing it right now. So I don't know, I don't understand that unless people have a problem that they don't have access to internet, because 2 times I have tried doing it from the class, there was an issue in the internet. We can try it next class. So you have to let me know that how many students are going to show up. Is
Sir,
there yeah.
you can select a class where the internet is stable, like the Audi or any class in Tabba or Aman.
Okay, I will have to find a classroom.
So my only issue is with online classes is that I can't seem to concentrate or understand the concepts that you're teaching. And even with my other classes, I take all of them physically because I can't.
Let me think about it. Okay, let me
Okay, sir, thank you.
stop recording here and I'll just see what can be done.